Record. All right, so just so you know, this is being recorded. This first video is just going to essentially talk about the course, how it's set up, what you can expect throughout the course, and then I'll go through the first week's kind of material. Let me pull this over here. This is our course, MAT125. You should familiarize yourself with this course. Make sure that you understand where to find the materials that you'll need. If you scroll down, there's a start here. You'll want to click there. The syllabus is here. The announcements can be found here. And all of this can also be found on this left menu as well. So if I go into modules, all of the course information is here, right? This very first module is just called course information. You'll want to make sure that you do this academic integrity statement that will open up some things down below that you won't be able to access otherwise. The course textbook is found right here. And then the formulas and conversion sheet that you'll be able to use on your exams is found here as well. And then you'll want to go through this Respondus practice quiz. Your exams will have a proctor program running. And this Respondus quiz is kind of a practice to make sure that everything's set up correctly, so that if something does go wrong, it goes wrong here and not while you're trying to take a test. In the first week, we'll be going through Module 1, Rounding and Estimation. So that's where we'll start today. And there's going to be typically homework and discussions for every week. This week's discussion is an introduction. I saw that most of you have gone in and done that. And if you haven't yet, you'll want to get in there and make sure that you write your introduction and respond to other students. Your readings are here. If we click on readings and resources, there's a couple of videos that are loaded up in here. The first one's for the estimations, graphs, and mathematical models, and the other one's for problem solving. Right? And then below that, there are PowerPoints that you can access to look at some of the material. And then your required readings, you click here from the book. It just tells you what to read. In this case, section 1.2 and 1.3. And if you click next down here, it'll take you to the next item in those modules. So in the next module, the next thing in here is those introductions. So I'm going to click back into modules and get out of here. Scroll back down here. Your homeworks are here as well. There's two homeworks. The first one is just a basic math assessment. The second one is an actual kind of homework. They've named it Homework Part 2. And then you'll have these questions, kind of like another little homework, but like kind of a quizzy type thing. And then an actual quiz. And you'll have those at the end of every module. Right? So let's dive into the material for this week. Let me get this out of here. The first thing that we talk about in section 1.2 is estimation. And they talk about estimation with rounding to begin. So we have perhaps large numbers, perhaps not so large numbers. But if I have something like, say, if I open up my bank account and I'm not me, but somebody else, and I have, let's say, $327,984,297, right? At some point, a lot of these digits just don't matter, right? If I put another dollar in my bank account and I have this sitting there, does it really matter, right? Does the difference between this number and this number matter? Does it make a huge difference, right? And I would say no, probably not, right? And even if I put an extra $100,000 in this bank account, it's probably not going to make a huge difference in the way that I view the number, right? So I would typically round this, right? So I would round this number. We'll take this first number to, and at some point, well, 3 or 4 digits in, it starts to just not matter. So I'm going to say I'm going to round this to the nearest $1 million. So I'm going to look at the millions place, which is this 7. I'm going to get this other number out of here, just out of our way. But this 7 right here is in the millions place. And to decide if I'm going to increase that or keep it the same, I'm always going to look at the next digit, right? If the next digit is 5 or more, oops, that's not helpful, 5 or more, then I increase, right? Which it is. The next digit here is a 9, so I'm going to increase this. So rounded to the nearest $1 million, that's 320, that 7 increases up to 8, and then everything else just gets zero filled. So again, if I'm looking at my bank account and I've got all of this money sitting in there, I'm going to say that I have somewhere around 328 million, right? And mathematically, we have a symbol that denotes about or around, and that is an equal sign, but it's kind of a wavy equal sign. So it looks like that, 2 little waves, and so I would say that this is about 328,000, or sorry, 328 million using that symbol. So it's important to know your places, your place names. Let me clear this out here. So if I have, let's say, a very large number, right? Each one of these has what's called each one of these is a period. Each one of these little 3 sets of numbers is a period. This is the ones period. The next one is the thousands. The next one would be the millions, and then the billions, and then the trillions. And they keep going up, quadrillions, quintillions, so on and so on. When you get to humongous numbers, there's things like called vigintillions, and nobody cares. Once you've got past trillions, these numbers are mostly too much for the human mind to even comprehend the largeness of them anyway. But they do keep going forever and ever and ever. But in each one of these periods, we have certain places, like the very first one is the ones, the middle one is the tens, and then the leftmost one is the hundreds. And that just repeats, right? But in the ones period, we typically don't say the period when we're in the ones. This 7 is simply just in the ones place. This 2 is the tens place. This 2 is the hundreds place. They repeat. This 5 is in the 1,000s place. Once we move over, we start indicating the period. This 9 is in the 10,000s place, and this 8 is in the 100,000s place, and then so on and so on. So this 4 would be in the 100 billions place, right? So when they ask you to round to some specific place, you need to know exactly where that is. And if I want to round this number that I've written up here, to the nearest, let's say 10 billions, Then again, I'm going to identify where that 10 billion is. That's a 6. And I'll always look at that next number. If that next number is a 5 or greater, I'm going to increase the number in the 10 billions place. But in this case, it's not, so I don't increase it. So I would say that this number is about, and again, I would use the squiggly equals 291 trillion, 400. The tens billions place doesn't increase, so it just goes to a 6. And then I zero everything else after it. And that's how we round, right? We can round numbers before multiplication to estimate. If I'm asked to take 32 and multiply it by 49, I don't know what that is. I can't do it in my head, right? I could grab some paper. I could, work it out. But if I want to estimate this, I'm going to round this first. So I'll round 32 to the nearest tens and 49 as well. And then do the multiplication. So rounded to the nearest 10, this becomes 30 multiplied by 50, right? 32 rounds down to 30, 49 rounds up to 50. I have 30 times 50. I know that's going to be 1,500. So I know that 32 times 49 is somewhere around 1,500, right? If I need to know exactly, I'll write it down, I'll work it out, but I should know just by this estimation that 32 times 49 is somewhere around 1,500. In this module as well is some graphs. So we introduce some graphs. We have the circle graph example here, Americans' definition of old age. Right? And let me grab this bit here. Oops. Get this, there we go. So do we have an example that refers to this graph? Example 5, applying estimation techniques to a circle graph. According to the U.S. Census Bureau, in 2020, there were 249,019,818 Americans 25 years and older. Assuming the circle graph on the previous slide is representative of this age group, use the graph. The rest of the question was weirdly cut off. Use the graph to determine a calculation. Oh, this isn't doing what I want it to. There we go. Use the graph to determine a calculation that shows the number of Americans 25 years and older who define old age by decline in physical ability. So the decline in physical ability we find here, oops, that's not a highlighter, that's not helpful. Boink. We find right here, decline in physical ability is 41%, right? So the true value they're looking for is 41% multiplied by this number 249,019,818. But again, that's a lot of work, and don't really care about all the way down to each individual person here. I probably only care about the thousands, right? So I'm going to estimate this by rounding. And in this case here, I'm going to round the number of people in here to the nearest 1,000. So that would be 249. Sorry, not thousands. I said 1,000. What I meant was not 1,000, million. Okay. Because that's all I really care about. Once I get the number of millions of people, I don't really care about how many extra thousands are hanging out there. And then I'm also going to probably round 41% to the nearest 10. So that would turn that into 40%. Right? So I know I'm going to be off, and that's fine. It's not going to be the right answer. It's not going to be exact, but I don't care. I'm just getting a ballpark figure here. So I'm taking 40%. And if I take 40%, I'm going to convert that into a decimal. So that's going to be 0.40. And then I'm going to multiply that by 249,000. Sorry, I keep saying thousand. It's million. 249 million, right? And that way I've got a fairly easy math problem to do. I can do it in a calculator if I want. I can do it on my worksheet here. I'm just going to take this 249, multiply it by 0.4. 9 times 4 is 36. 4 times 4 is 16, plus 3 more, 19. 4 times 2 is 8, plus 1 more is 9. There's one decimal here, so it's 99.6, or 99 million people. Sorry, 99,600,000. And again, it's close enough, right? If we wanted to round this to the nearest million, this would be 100 million. And so our answer should be in that ballpark. If I actually do the math out here, let me just grab a calculator on my other computer. So 249,019,818. I get 1 million. So the actual answer is 1,020,981. What did I write here? 0,249,019,818. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's not that. I'm putting my decimals wonky. Sorry. My calculator doesn't put decimals, so I read it weird. 102,098 and 125. So that's the actual answer. There's a decimal there, but again, you can't have half a person, so I'm going to round that to the nearest person. But it's close, right? It's not that far off. It's in the same ballpark, and that is estimations. Right? We can also take a look at some bar graphs. We'll have some bar graphs in section 1.2, and then also in those, this bar graph comes from the PDF in the module 1 itself. So if I look at these, the life expectancy here in the United States by year of birth, males are in that red and females are in this amber color, right? We can estimate a male's increased life expectancy So we're asked here, estimate a male's increased life expectancy rounded to the nearest hundredth of a year for each subsequent birth year. Right? So what I'm going to do, we're looking at males, that's this red color. I'm going to take one value down at the very bottom and then the value at the very top. Right? So to estimate his increase, I'm going to find the difference between the increase and then divide it by the number of years that that increase happened over. So I'll take that very top value of 77.1, and this is in years. So 77.1 minus 65.6, and then divide it by the difference here between the year 2020 minus 1950. And here I get, if I calculate this, I get 0.1642 And this goes on 1, 6, 4, 2, 8, 5, 7, goes on forever, right? But I really am only interested in the nearest hundredth of a year. So the hundredth place is the 6. And so I'm going to round it to that place by looking at the next digit. The next digit is not a 5 or more. So I'm going to say that this is near 0.16, which means that every year after 1950, the average male's life expectancy went up by 0.16 or 1600th of a year. And if I'm asked to estimate the life expectancy of a man born in 2030, right, I can say that I'm probably going to start here at this 65.6, right? An average man was expected to have a life expectancy of 65.6 years, plus 0.16 multiplied by however many years past 1950, which I can say in mathematical terms, this would be 65.6 plus 0.16 times x, where x is defined as the years past 1950. So we're looking at the year 2030. Well, 2030 is 80 years past. So I'm looking at 65.6 multiplied by that increase of 0.16 multiplied by 80 years. And again, this ends up being 78.4. Right. Which again, this is kind of an estimate, right? It's an average anyway, but it's also an estimate of that average. And so we could say that this is probably somewhere in the neighborhood of 78.4. And if I look at 2030, oh, just kidding, that's not on the map. But that would be our next one here. And you would expect it to be just a tad bit higher than the decade before. What we can also note, if I can grab this and move it out of my way. Oh, just kidding. Grab it again. Is that if we, again, just look at the males, since that's what we did our math on, I can think of each one of these values as a point. The very maximum value is just a point. And I can probably create a nice straight line that's close to all of those points, right? And sometimes those graphs, the graph doesn't go in a nice, beautiful straight line. Sometimes there's all sorts of up and down. So rather than looking at it as one line, I can look at it as several lines. The line between the first one here, and then the line between the next two. And I'll try to make these straight. Sometimes they don't like to play. All right. Right. And what we're looking at is then, rather than looking at all these bars, looking at the graph itself, we're just looking at that line. And sometimes those lines can be a little bit more crazy, but this is essentially that top line, and we get rid of all that bar graph below, right? And it's nicer to look at this. I can tell just by looking. In this particular case, this is cigarette use by US college students between 1982 and the year 2020. I can tell, right, in 2020, my value is right here. Reading back, that value is 8%, right? Reading the value for, let's say, 1990, comes back over to here, so maybe 21%, something like that, right? And I may not be able to tell exactly, but you know, it's pretty close within these values and a not very large range that I have to guess between. Right? So this is a line graph. A lot of times these are a lot easier to play with, right? For example, if we're asked some questions, that's not what I want. That is humongous. In which year did 30% of college students smoke cigarettes? Well, let me clear my junk out of here. And it's fairly easy, right? 30% is a number on the left. It's between 28 and 32 here. And that value right there corresponds to the year 1998. You might also be asked things like, what percent of students smoked? In, let's say, 1990. So I look at 1990 and I'll follow the graph upwards until I hit the graph itself and then drag that to the left here. And it's a little bit more than 20, maybe not quite 21%. I would say maybe around 21%-ish, right? 20 and a half, 21, something like that. And then we talked about models very briefly, but a model a mathematical model is designed to estimate some value or predict a value. For example, I have a model. This mathematical model aims to estimate or project the average cost of tuition and fees for the school year ending in 2030 at a public college, right? So, oh, I cheated. I grabbed the wrong one. Zoop. Yoink. This one is what we want to look at to start. So we're asked to write a mathematical model that estimates the average cost of tuition, fees, and at a public four-year college for the school year ending in the X years after 2000. And they gave it to us here. They didn't give us enough information to create this our own, so they gave us the model itself, but it's $3,349 plus 300 multiplied by X, where X is years after 2000. So we have our model, it was given to us, and we're asked now to evaluate, right, for the cost of tuition in the year 2030. So if X is the years after 2000, then X becomes 30 because there's 30 years after 2000. And we just plug it in, and 30 times 300 is 9,000. You add that to the 3,349 and you get 12,349, right? So we can predict values using these models. Another one is that can I type this? The temperature outside in Fahrenheit is how many cricket chirps you can hear in 15 seconds plus 40. So if I count on some night 15 cricket chirps in the 15 seconds, and the question is, what is my estimated temperature outside? So my equation then is the temperature is the number of cricket chirps that I count, that's my x, that's my unknown, and I add 40 to it. Since I've counted 15, that replaces x, and so the temperature for me is 15 plus 40, that would be 55 degrees. So this is a mathematical model. It's used to simply evaluate or estimate or take an educated guess at the value of something. And again, that's 1.2 in kind of a nutshell. You'll make sure that you want to go through your book. There's a little bit more information in there. And then you can always ask me questions as well. But we'll move on and talk about 1.3 here. But 1.3 is largely on Polya's 4 steps problem solving. So Polya was just a guy that came up with this, and it's used in almost every learning situation or learning environment ever. But he's got a 4-step problem solving approach. The first step is to make sure that you understand the problem. Which means you want to read through the problem, make sure that you understand what they're asking, and make sure that you understand the information that you have, and if you have enough information to solve the problem, right? But before you try to write anything down, read through the problem. At the end of the problem, if you ask yourself, what are they asking me, and you don't know, read the problem again, right? So step 2 is to devise a plan. Right. That is, you'll want to look for patterns, look for information that you have, and then create a mathematical model, if you can, to express the situation. A model or some equation that represents the problem. And then our third thing is to carry out and solve the problem. Carry out the plan. Solve any equations. And then state the solution in terms of the problem itself. And then the fourth, and it's very easy to skip the fourth, but it's not always a good idea too. The fourth is to look back, check the answer. And importantly, to make sure that it makes sense. Every once in a while, we'll get problems that are like something like Annie was, 12 years older than her daughter when her daughter was 3 years younger than something or other. And people will create an equation and they'll solve it and they'll say, oh, Annie was 12 and the daughter was negative 14. Probably not. Probably not a valid solution, right? So make sure that it makes sense. Make sure that the numbers don't, get all sorts of out there, and that you can state the solution to the problem in terms of the problem itself. Right? So let's take a look at a few things here. If I give you this question, a man purchased 5 shirts, each at the same discount price. How much did he pay for them? What is it asking you to do? Well, the question here is, how much did he pay? And the information that we have is that they were all the same. And that's really it. That's all my information. There's nothing else that I can infer, that I can assume, or that I can get from this problem other than every single one of these he paid the same amount. It was a discount amount, but that's it, right? And so the next question is, do I have enough information to solve this? And no, clearly I don't. So there is no model to be created here, right? I just have this guy bought 5 shirts. Cool story. How much did he pay? Couldn't tell you. No idea. All right. This one here, let's look at by paying $100 cash upfront and then the balance at $20 a week. How long will it take to pay for a bicycle that costs $680? Okay, so this, to understand what's happening here, the question that is being asked is how long, right? Some amount of time. I need to know how long it's going to take, how long specifically to pay off this bike. Which means my answer shouldn't be $7. It shouldn't be any number of dollars. It shouldn't be anything other than an amount of time, right? Weeks. In this case, we're talking about $20 a week. Our answer is probably going to be a number of weeks, right? So the information that I have is that the total cost is $680. Right? I'm going to pay up front $100, and then I'll make weekly payments of $20. So I need to create some sort of plan. I need to create an equation that describes this. So I would say that I want to first find out how much I have to pay off. Say the balance. After my $100 payment, So that's easy. That's $680 minus $100 is $580. And if I'm making payments of $20 per week, I can just take this $580 and divide it by the amount that I'm making. So I take this $580, I divide it by $20, or sorry, not 20. Sorry, $20 per week. And this is 29. And so it should take me 29 weeks to pay off this bike. And that's it. In the end, how long? My answer is in weeks. It's 29 weeks. Does that make sense? You can try it. You can say 29 weeks at $20 is indeed $580 plus my $100 initial payment. That's my $680 paid off, right? Let's take a look at this one here. That's not what I want. All right, we have 4 runners in a 1-mile race: Maria, Aretha, Thelma, and Debbie. Points are awarded only to the woman finishing first or second. The first place winner gets more points than the second place winner. How many different arrangements of first and second place winners are possible, right? So here it's nice to create a diagram, right? I can write these names out, and I'm going to just copy and paste this. So if I have Maria in first place, there are 3 options for second place. Aretha can be in second place, Thelma can be in second place, Debbie can be in second place. And so I can write this as possibly Maria and then Aretha, and then Maria, Thelma, and then Maria, Debbie. And these are all 3 possibilities, right? I don't really care about third and fourth place because after second place, there's no prizes, so I don't care, right? But I have these 3 possible outcomes if Maria were to be in first place. So I could also have had Aretha win, and I have 3 possibilities if Aretha wins. I could have Maria in second place. I could have Thelma in second place, and I could have Debbie in second place, right? And so I'm going to write these as another set of first and second place winners. So AM or AT or AD. And I can keep doing this with all of these. I don't have to draw out this actual diagram every time. Thelma might win. And if Thelma wins, I could have Aretha in second place, or I could have Thelma and Maria, or I could have Thelma and Debbie, or I could have Debbie win with Aretha as a second place, Debbie win with Maria in second place, or Debbie with Thelma in second place. And all in all, this is all of them. So I have 12 total possible combinations. And if you wanted to, this is in the slide. It's not always convenient to shortcut it. In this case, I think it was, but you could also have listed them out in full, right? Maria, Aretha, Thelma, But I like my little shortcut there better. So that's kind of the gist of 1.3. Again, make sure you get into the book and kind of take a look there, and then get your homework. The sooner you start your homework, the better off, I think. That way, if you have any questions, there is enough time to get those asked and answered. Take a look around in the course itself. If you have questions, there is a discussion for asking your instructor, me, or you can just email me any questions that you might have. These meetings, I had a few people ask, this meeting that I have right now is not a mandatory meeting. You don't have to be here. It's good if you are here so that you can ask questions if you have any, but they all will be recorded so that you can view them whenever at your leisure. So open it up if there's any questions to anyone in the room. And if not, then that will conclude this one, and I will see you guys next time. Thanks.